Let's look at the different kinds of microbes we face and see what can be done about them. The four major classes of infections are viruses, bacteria, fungi and yeast, and parasites. Let's begin with viruses. Viruses are among the most dangerous infections that we, as a species, have to deal with. Unlike other microbes that are typically spread by vermin or insects, viruses can spread directly from human to human through a sneeze or a cough. Smallpox killed some 500 million people last century, and influenza another 100 million in the 1918 outbreak alone. Now, with overpopulated cities where people are in close proximity, and given the ease of international travel, a single major viral pandemic would be much worse. According to the Centers for Disease Control, if another major influenza pandemic were to occur today, estimates are for 1 billion dead. While researchers work furiously to develop antiviral drugs, a truly effective broad-spectrum antiviral medication still eludes them. But we don't need to look to the apocalyptic to see the effects of viruses. Viruses are vastly underestimated as a cause of chronic disease today. It's not just the millions who currently suffer from viral infections, such as hepatitis C, AIDS, and herpes that are affected, but the average man and woman on the street. Everyone, without exception, is infected with the Epstein-Barr, cytomegalovirus, and herpes viruses. Most people are strong enough to keep these viruses from being much more than a low-grade nuisance, but they slowly eat away at our vitality, taking advantage of us when we are tired or under the weather. They are among the many opportunistic infections that wait for us to let our guard down. What is also generally unknown is that many of the conditions currently considered to be genetic in nature are in fact viral in origin. How does this mix-up happen? Firstly, viral infections are virtually impossible to detect, so unless you know exactly what you are looking for, you are likely to miss them. Secondly, viral infections also have the ability to cause genetic mutations in our DNA. Thus, in some cases, the genetic mutation that a scientist points to as the cause of a disease is actually the result of a virus he cannot detect. Many people today who are told that they have incurable genetic diseases actually have very curable viral infections. If you are dealing with a disease of unknown or genetic origin, or are just feeling run down, odds are you're dealing with a virus. Even though modern medicine has yet to come up with a truly effective broad-spectrum antiviral medication, there is a natural way to directly attack viruses. First, you need to understand a little bit about how viruses work. Unlike all other life forms, viruses are unable to reproduce on their own. Viruses reproduce by commandeering the machinery of our own cells, turning them into virus-making machines. Our own cells end up making the very viruses that can make us even sicker. While this is a very clever strategy for the virus, it does have one exploitable weakness. In order for a virus to reproduce and make us sick, it must first enter our cells. As long as it stays outside our cells, it can't hurt us. This is where we should focus. How can we keep a virus from entering our cells in the first place? It turns out that many viruses use an enzyme called integrase to get inside of our cells. If we can inhibit the integrase enzyme, then many viruses won't be able to get inside our cells to reproduce. Now, back to our friend the raspberry. Ellagic acid, a compound made from raspberries, does just what we are looking for in our fight against viruses. Ellagic acid is an integrase inhibitor. If we take ellagic acid, we will be able to inhibit many viruses, known and unknown, from entering our cells and reproducing. Now let's turn our attention to bacteria. The antibiotic revolution made once feared diseases like tuberculosis, staph, and strep manageable and often curable. Well, at least they used to be. Massive overuse of antibiotics in hospitals and in livestock management has given rise to the superbug. The superbug is antibiotic resistant and very aggressive. The very bacteria we once thought we had beaten are now making a comeback and threatening to wreak havoc around the globe. Right now, 2 billion people in the world, or roughly a third of the world's population, have tuberculosis, and antibiotic-resistant staph and strep run unchecked through our hospitals, often infecting and sometimes killing patients who come in for routine operations. This is understandable. Bacteria reproduce so quickly and mutate so easily that developing resistance to any particular antibiotic drug was only ever just a matter of time. What we need is a way to stop all bacteria, not just one type or another. Moreover, we need to find a way to stop bacteria at a level that they cannot mutate around. The deepest level of any life form is its DNA. Is there a way to affect bacterial DNA without harming ourselves? It turns out that there is. Bacteria, like most life forms, coil their DNA molecule into a very tight ball. This coiling is required to fit the sometimes 10-foot long DNA strand into a tiny bacterial cell. That's right, DNA can be up to 10 feet long, and it has to fit in a cell 30 million times smaller than its length. Now, what would happen if we were able to uncoil that DNA strand? What if we could pull on it like the loose string on a knitted sweater? You guessed it, the whole coil would unravel. When the DNA is coiled up, the information is accessible, but in an uncoiled state, the DNA would be unreadable. In this state, the bacteria wouldn't have the information required to run its basic life processes. In other words, the bacteria would die. Here's an analogy to illustrate how this works. Imagine that you want to build your first house by yourself. Having never done this before, you decide to go to the library to get some books on basic carpentry and architecture. Unfortunately, when you get there, you find that a minor earthquake has knocked all the books off the shelves into a disorganized mess on the floor. You know that somewhere in that mess are the books you need, but it would take months to find them. It's the same when you unspool the DNA of a bacterial cell. The information, in this case the DNA, is still there, but it is inaccessible, and the bacteria dies, unable to get the instruction on how to maintain its basic life processes.